Semiconductors are having this nasty property. First understand, then try is a good advice here. You want to control a higher amperage with several transistors, or you're aiming to get more brightness using several LEDs in parallel. In theory this is possible, but in practice there is a vicious cycle causing things getting out of control. Using 1000 amp switching transistors for the experiment would be spectacular, but it wouldn't be particularly educational. Instead, we are explaining a graphical method helping us to understand semiconductors' behavior, and we are using standard LEDs. They are great as indicators or illumination in our maker projects. As a general rule, for several LEDs, each one needs a separate serial resistor. However, with several LEDs, this is becoming quite an effort. Is it possible to simplify this? We are relying on PCB to manufacture our PCBs. This makes electronics really fun. Regardless of whether you're creating a small beginner's project or working professionally, just take a look at PCBWay's websites. Take the easy way with PCBWay. Let's take a closer look at the green LED's datasheet. We are not recognizing it as a diode characteristic at first glance because of the logarithmic y-axis. I'm transferring the values to an Excel sheet, and with a linear axis, the LED's forward current characteristic looks like from a textbook. Now comes the hack. This line is representing a series resistor in the diagram. Here's the maximum current, calculated by the supply voltage divided by the resistance. In our case, 220 ohms divided by 5 volts. The other point equals the supply voltage. The intersection of the two curves is the operating point for our LED. Why? Simply because equal current is flowing through elements connected in series, in this case about 8 to 9 milliamps. By the way, the series resistor can be dimensioned from the supply voltage minus the LED's forward voltage divided by the desired current. Now let's see what happens when we connect a red LED in parallel. As soon as I'm plugging the red LED, the green one stops working. Why can't we operate both LEDs at the same time via one series resistor? Here is the data for the red LED from the corresponding datasheet. With the red LED connected, the operating point is moving here because its forward voltage is significantly lower than from the green one. At around 1.8 volts, the green LED doesn't light up because it's practically drawing zero current. Instead, the full current is flowing through the red LED. So, the first conclusion is that we cannot operate LEDs of different colors in parallel. Okay, but could you operate LEDs with the same color in parallel? Given that the two LEDs had identical characteristics, 50% current would actually flow through each. Unfortunately, the characteristics are not exactly the same due to manufacturing tolerances and temperature differences. This is the LED's forward voltage over temperature at 20 milliamps. Assuming its principal shape remains the same, we can estimate characteristics for other temperature ranges. The green line is the characteristic at 25 degrees, the green-blue line is for 0 degrees, and the green-yellow line applies to 60 degrees Celsius. If we were to operate 3 green LEDs in parallel at the temperatures mentioned, they would shine with different brightness, as we can estimate from the currents. The effect is already apparent when I warm one of the 2 LEDs with my fingers. The warmer one is shining a little more brightly. While this effect can be tolerated at low power, it's causing the arrangement to run out of control at high power. Assume we are operating 2 LEDs at maximum current and one has a slightly higher temperature than the other. Then this is causing less current flowing through the cooler LED and more through the warmer one. As an effect of this, the warmer LED gets warmer and warmer, while the cooler one draws less and less current and continues to cool down. Eventually, the full current intended for 2 is flowing through one LED, which is destroyed from that. Next, the full current flows through the second LED, destroying it too. So, if you want to operate semiconductors at their performance limits in parallel, you have to keep an eye on tolerances and temperatures. The graphical method can be very helpful assessing that problem. Series resistors for each element are compensating for the negative temperature coefficient, and the current is evenly distributed across all transistors. However, the power efficiency is suffering from that. But there is also some really good news I didn't expect. At low power, parallel connection of LEDs is feasible. I connected 5 LEDs in parallel, trying 5 different colors. Sometimes at very low current, they are not exactly shining at the same brightness, as you can see here from the blue LEDs. However, at normal brightness, you don't see any difference. That is saving me a number of serial resistors for the illumination of a project using several white LEDs. Are you having experience with parallel connected semiconductors? Write me in the comments. Parallel connection is okay for operating same color LEDs at low current. Actually not recommended in the textbook, but possible, because LEDs today's manufacturing tolerances are small. At high current, however, it can be dangerous for semiconductors in general. Negative forward voltage temperature coefficients are driving the arrangement out of control. In case your supply voltage is high enough, connecting LEDs in series is the solution that even saves energy. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.